Welcome to Unit 6, Section 2. Today we're going to take a look at radicals and rational exponents. You might be thinking to yourself, what the heck are radicals and rational exponents? But before we jump in, let's quick talk about what we learned yesterday. Yesterday we looked at powers, expressions like 5 squared that had a base and an exponent. And we said 5 squared is really just 5 times 5. And you know, or you're pretty familiar with, 5 times 5 is 25. Well, the inverse of these exponents are radical and rational exponents. So a radical would be something like the square root of 25. And the square root of 25 is just asking what number would you multiply by itself 2 times to result in 25. And you would say, oh, that's 5. So the square root of 25 is equal to 5. And that's what a radical expression is. Now there's more than just square roots. There's things like cube roots and fourth roots, and that's what we're talking about today. So here's another example. 2 cubed is 2 times 2 times 2. The result is 8. And therefore the inverse of that cubing process is known as the cube root. And here's the radical expression for it. The cube root of 8 is equal to 2. It's essentially just asking what number do you multiply by itself 3 times in order to get 8. Likewise, the fourth root of 81 is equal to 3, because 3 times 3 times 3 times 3, 3 times itself 4 times, is the result of 81. Alright, so there's some rules around nth roots of a number a, and in order for them to be real numbers. So first of all, if n is odd, then a has one real nth root. We're going to give you an example of this. The third root of negative 27. That would be written as the cube root of negative 27. That has one real solution. All right, and that real solution in this case would be negative 3. However, if n is even and a is positive, it's greater than 0, then it has two real nth roots. Here's another example. The fourth root of 81. Just like what we did above, right? Fourth root of 81 is actually equal to both positive and negative 3. Because not only can you multiply positive 3 by itself 4 times to get 81, but you can also multiply a negative 3 by itself 4 times and still end up with a positive 81. Because a negative times a negative times a negative times a negative is still a positive. Next up, we got if n is even and a is equal to 0, then a has one real nth root. The example here is the sixth root of 0. What do you multiply by itself 6 times in order to get 0? Well, you guessed it, it's just 0. And then finally, if n is even and a is less than 0, that means it's a negative number. Then a has no real nth roots. Here's another example of that. The fourth root of negative 16, not a real solution, not a real number. Now there's actually a solution for this. You're going to learn that in upcoming math courses, but for now we're going to say it's just not a real number. All right, let's jump into examples here. We want to find the indicated real nth root of a. Here we have the cube root of negative 64. Well, we got a negative number here. We're taking the cube root, that's an odd number. Therefore, I know there's one real solution, and that's got to be negative 4. Next up, we got the square root here. That's the second root. And the square root is actually a unique radical. You do not need to write the little 2, which is called the index number. The square root of 81, and since this is even, that's positive, there's both a positive and negative solution, and that's positive and negative 9. So when we evaluate expressions with rational exponents, we say that the radical, the square root of a, indicates the positive square root of a. All right? And the radical nth root of a, where n is even, indicates the positive nth root of a as well. Now that's when we're solving equations using radicals. All right, next up, we want to evaluate each expression. We got the fourth root of 81. Remember, this is the even index number, positive, so there are going to be two solutions. This is both positive and negative, positive and negative 3, not 31. All right, now we have the opposite of the fourth root of 81, so that's the opposite of positive and negative 3, which is just negative and positive 3, so it's still the same solution. All right, now I'm going to take the cube root of negative 8. We can do that. We have an odd index number with negative. The cube root of negative 8 is just one solution, and it's negative 2. Finally, we're going to take the fifth root of 32. This is an odd and positive. Again, that solution exists. There's just one of them, and that's just positive 2. All right, let's take a look at rational exponents. Now, rational exponents are a way to write radicals using an exponent form. So you see here that we have this base, a, and I'm going to write it over here, to the rational exponent of m over n. Now, what this is telling me to do is it's actually telling me to take the base m, or a, and raise it to the nth power, but then take the nth root of that. So to simplify what we got going on here, the numerator is my exponent, it's my power, and the denominator is my radical, or in other words, my root. So another way to see this is to write this in radical expression. I'm going to take the nth root of a to the m power. Now, it doesn't matter what order you do that in. You can take the nth root of a and then raise that result to the mth power, or you can take the nth root of a to the m. So to rewrite this radical expression, the cube root of 9 squared in rational exponent form, it would look like 9 to the 2/3. Remember, the 2 is my exponent, it's my power, and that denominator 3 is my radical. Let's practice evaluating each of these expressions. I have 36 to the 1/2, so that means I am going to take the square root of 36. Hey, pretty unique thing to learn here, that whenever you see that 1/2 exponent, this is really just the square root. All right, square root of 36 is just equal to positive 6. We have 25 to the 3/2 now. Remember, 3 is my numerator. That's going to be my exponent, and 2 is my denominator. So I'm going to take the square root of 25 and raise that to the 3rd power, or my 3rd exponent. So that looks like this, square root of 25, and then I'm going to raise that to the 3rd power. So that gives me 5 cubed, and that's 125. All right, next up I have now 64 to the 2/3. Again, 2 is my exponent. Actually, this is different than the previous one. The exponent 2 is going to be, I'm squaring something, but that's after I take the cube root. So I have the cube root of 64, and then that result will be squared. Well, the cube root of 64 is equal to 4. 4 squared is equal to 16. All right, in our next example here, we got the radius of a sphere, and it's given by this equation. Radius is equal to 3b divided by 4 pi, all raised to the 1/3 power. Hey, 1/3 power really just means we're taking the cube root of that result. All right, so find the radius of the basketball to the nearest inch when the volume is 463. All right, so we are going to substitute in what we know. We got 3 times 463 in our numerator, and we're going to divide that by 4 pi. And then the result of that is going to be taken to the 1/3 exponent, or the cube root. All right, another way to write that is the cube root of this entire expression, 3 times 463, all divided by 4 pi. Now there's a little bit of a trick to doing this on your calculator, so let's grab our graphing calculator. All right, there are 2 ways to enter this into our graphing calculator. The first way we're going to take is the cube root, so press on your math button here, and we're going to go down to number 4 that says to take the cube root. All right, this is the cube root of our expression. Now we're going to open up a set of parentheses for our numerator, and it was 3 times 463, and then we're going to close that up and divide it by, now once again we need to open up a set of parentheses and hit 4 pi. Now our pi button is above this little up arrow, so we're going to have to press second function, little up arrow, and close our parentheses. Now you can see that we're going to take the cube root of this quotient. Go ahead and press enter and you'll get 4.8. Now the other way of doing this is to do our division first. So we'll actually open up two sets of parentheses and do our 3 times 463. Oops, sorry. 463. Close one set of parentheses, divide that by, and we have to open up another set of parentheses. This is very important. Your second set of parentheses here have to include the 4 pi. That will give you your denominator as that product of 4 pi. Close one more set of parentheses. Now we are going to raise this to this little up arrow here, the 1/3 power. So 1 divided by 3. Remember, this represents cube root, and you can see that you'll get the exact same answer. All right, so the radius here of our sphere is equal to 4.8, and our units were inches. Next up, in example 5, to calculate the annual inflation of an item that increases in value from P to F over a period of n years, you can use this equation. R is equal to F divided by P, all to the 1/nth power minus 1. Find the annual inflation rate of a house that increases in value from 300,000 to 360 over a period of 8 years. All right, so using our formula and plugging in what we know, remember it's increasing from P to F, so we have 360,000 being divided by 300,000, all raised to the 1/8 years is the number of years. That's our n value, so 1/8 minus 1. All right, going back to our calculator here, we'll enter in our quotient of 360,000, divide that by our 300,000, and now we can raise that to our 1/8 power. And from that, we will arrow over to the right and subtract 1. And our percentage of inflation is, well, I'm sorry, our decimal for inflation is 0.023. Now, 0.023 is our rate of inflation over that year. So that corresponds, we got to slide that decimal place 2 places over to the right. That corresponds to 2.3% inflation.